Hello and welcome back. In this video, we're going to be taking a look at ray diagrams for biconvex or converging lenses. A couple things to understand about how lenses work differently than mirrors. Mirrors reflect the light. Lenses refract the light. Now, I can pass light through the left side of this lens, directed to the right, and it would converge through that far side focal point. But I could also pass light from right to left, in which it would converge through that far side focal point. In other words, lenses, yes, they refract the light instead of reflecting it. There might be some partial reflection, of course, but they mainly refract the light through focal points. And since they can refract light from both sides, they have two focal points. Now, the focal length, which is the distance from the focal point to the lens, will be the same if the curvature is the same. The rules are very similar for lenses as they are for mirrors. Ray 1 goes parallel to this thing called the principal axis and refracts through a focal point instead of reflects through a focal point. The second ray will go through a focal point and then refract parallel instead of reflect parallel. And instead of going through the center of curvature and reflecting upon itself like a mirror would, the third ray goes right through the center of the lens unrefracted. Let's take a look. Now, in any of these problems, you really only need to draw two principal rays to locate an image. Where two rays intersect, that's where the image is formed. If the arrow we draw from the principal axis to the intersection point is upside down, that means the image is inverted. If it's right side up, it's upright. If the image is a longer arrow than this object over here, then it's an enlarged image. If it's smaller, it's a reduced image. Now, to be a real image means that the image is projectable on a screen. So say this line represents a screen. Now, since images form on the other side of lenses, and I can project those images on a screen, real images would form on the far side of lenses. Virtual images, therefore, would be found on the near side. Near side meaning the same side as the object, far side meaning away from the object. Let's take a look at example number 1. We're going to take the principal axis, we're going to take the first ray and go parallel to the principal axis, which is this line here that bisects the lens, and we're going to refract it through the far side focal point. And when you do this, draw the refracting ray as long as possible because you don't know where intersection is going to occur. Now, just like we did with mirrors, anytime we drew a reflecting ray, we always drew a back ray extension. A back ray is a virtual extension of the reflected ray. Well, refracting rays also have a virtual extension. So we're going to draw a back ray directly back from any refracting ray. So all refracting rays are going to have back rays. Let's just kind of label what we have so far so we can get a better sense of this. This would be my incident ray. Right? A good way to remember this is that this is the ray coming in to your lens. So the incident ray is the black ray. The blue ray, that's the refracted ray, not reflected, refracted ray. And the gray one, well, that one's going to be what I term as a back ray. It's really more a virtual extension of the refracted ray, but I call it a back ray just for simplicity. And that's what ray number 1 looks like. Ray number 2 is the converse of ray number 1. If ray number 1 goes parallel and then refracts through a focal point, the converse of that statement would be to go through the focal point and refract parallel. So that would mean we are going from the object located over here through the near side focal point that's unused. And as soon as we get to the lens, we then refract parallel. just like that. Remember to draw the back rays from your refracted rays. Okay, already you can see your two refracted rays have met, so you know your image is going to be right there. But let's do the third ray and see what that one looks like. The third ray goes from the top of the object, go right to the center of the lens, and aim for that point right there. As soon as you get there, keep going unrefracted, just like that. Okay, and you'll notice the black and blue line just keep going in a straight line. I just changed it from black to blue to show you the refraction. The refraction happens on the right side, the incident rays are on the left side. However, that third ray is really unrefracted. Now, I still am going to draw a back ray for it, but the back ray is going to have to be drawn way back over here, away from the object. Okay, you can see that all three of your back rays have diverged. You should also be able to see that your three refracted rays have converged. And that convergence is the location of the image. And so we would draw an arrow down to the point of intersection from the principal axis. And we would identify the characteristics of this image as an inverted, reduced, because it's smaller, real image. Now, for the remaining problems, I'm simply going to use the first ray, which works for any lens at any distance away from the lens, and the third ray, which goes right through the center of the lens unrefracted. Let's take a look. In number 2, I'm going to go parallel to the principal axis. And refract through the far side focal point. Since I don't know where the intersection is occurring, I'm going to draw it long. Then I'm going to go through the center of the lens. And I'm going to stop when I get to the center of the lens. And I'm going to keep going unrefracted. And you can see that my arrow shows up around there. And it's an inverted arrow. It's roughly about the same size. So I have to kind of write that in because it's not an option. And it's a real image because real images form on the far side of lenses to be projectable on a screen. Well, in number 3, you can see the object is moving closer to the lens. So now we're a little bit closer. We're halfway between what would be deemed as the center of the lens curvature and the focal length. We're going to go parallel to the principal axis, and we are going to refract through the far side focal point. Do that nice and long because we don't know where intersection will occur. Then I'm going to go through the center of the lens, just like that. And I'm going to keep going. And you can see, and then I can draw the back ray extension this way. You can see the image itself is going to form at that convergence way over here. Extend the principal axis to produce an inverted, enlarged real image. In example number 4, the object has been placed at the focal length. Let's see what happens. We're going to go parallel to the principal axis, and we're going to refract through the far side focal point. There we are. Then we're going to go to ray 3, which goes right through the center of the lens, unrefracted, meaning we just keep going. And I'll draw my back rays for both. You should notice, ladies and gentlemen, that we end up with a parallel set of refracting rays and back rays. This is a unique situation. You must have either refracting rays intersect or you must have back rays intersect in order to produce an image. Since no intersection occurs, no image is formed. This was similar to objects placed at the focal length in front of a concave mirror. We also saw a similar case where no image was formed. And now in question 5, we're going to take a look at what happens when the object moves inside the focal length. Again, start with ray 1, parallel to the principal axis. Stop when you reach the lens, and then refract through the far side focal point. Draw your back ray. Okay, then I'm going to draw my third ray. So I'm going to go right to the center, aim for the center. And I'm going to keep going, unrefracted. Now you'll notice that this one has a back ray that's intersecting. You can see that the two sets of refracting rays are diverging. But you should also be able to see that the back rays are converging in this one, producing an example of an upright, so we have a right side up arrow, enlarged, the image is bigger than the object, virtual images. Real images happen on the far side, virtual images happen on the near side. This would be a perfect example of a magnifying glass. If I take a magnifying glass and I put it really close to an object, I end up getting an object that's bigger and upright. In the next video, we're going to take a look at how to do ray diagrams for biconcave or diverging lenses.